Hey guys, welcome back. We're going to try our first lesson here with our remote learning, and starting our last unit of the year, we're finally looking at statistical inference. All of the tools that we've learned up to this point this year are going to come into play. We'll see some things kind of reminiscent of some of the tests that we've done earlier this year when we looked at chi-square at the end of the first semester. But that specifically was looking at categorical variables. In this unit, we're going to be focusing a little bit more with the quantitative or the measurement variables. But the procedures you'll find in the coming lessons are pretty similar to what we did back with chi-square. But to build up to that, we have a little bit of work with some of the techniques that we'll be using as part of those tests. So we start with looking at sample distributions, and specifically today, sample proportions. So you can see our target there: calculate sample proportions and relate them to the normal distribution. These notes are at the top of the page for our daily lesson. There's also a formula or equation sheet that we'll be using throughout this section there. If you want to reference that, we'll be looking at a couple equations today. And there's also a rule sheet for the conditions that we'll be using when we talk about today. So those are all attached at the top of this page today. So we'll start with one quick warm-up, kind of blending in some of the ideas that we started with in probability. Let's say that there's 40% of a large population that disagree with a new law. Now think about the role of a sample size here. Let's say if we took a sample of only 10 people, what's the likelihood or the probability that exactly 40%, 4 of those 10 people, will disagree with that law? Okay, would you be surprised if only 2 people in that sample of 10 disagreed? What about if none of them disagreed? Well, probably not, because you know that 10 is a relatively small sample size. So if there's any variation at all, like differing by 2 people or differing by 4 people, that changes that percentage rather dramatically. But looking ahead at part B, now if that sample was 1,000 people, so 40% of them is 400, okay, you know that there's no guarantee that from that sample exactly 40%, 400, will disagree, but you'd expect something pretty close to that. Okay, would you be surprised if only 200 in that sample disagreed? Yeah, probably. I mean, now you're looking at a change of 20%, but that change is meaning that 200 people are further away from what you expected across 1,000 people. And would you be surprised if none of the people disagreed? Yes, that would be extremely impossible. Okay, talking about those odds of, like, I don't know, winning the lottery, that sort of thing. So it theoretically could happen, but it would be nearly impossible for something that far away from what we would expect to have occurred. So when we look ahead at letter C, explain how the long-run relative frequency interpretation of probability and Gambler's fallacy help you answer these questions. Well, you know that long-run relative frequency, whatever happens in the long run, there's no guarantee that that exactly is going to happen in the short term. Okay? And that Gambler's fallacy kind of plays into that. Sometimes people think that long-run relative frequency must happen in the short term. And we talked a lot when we were back in school about that misconception and leading to some bad decisions sometimes. So keep those things in mind as we progress with our work today. That whatever happens in the sample, okay, that's a subset of the population. Just because the population has a mean of this, or across the entire population, for example, 40% disagree with this new law. If we were to take a sample from that population, there's no guarantee that exactly 40% would disagree with this law. So in the big picture, in real life, we are using the sample to say something about the population. We're working backwards from the sample to the population. Okay, so from that population, you're collecting a sample. And remember, in the first semester, we talked about all those sampling techniques. And you're measuring some variable of interest. Okay, typically that's a proportion. It could be a mean if you're looking at some quantitative data. So you're answering that question for the sample because you don't want to do a census and survey every single person in that population. Now, with statistics, you're determining how close that answer from your sample will be to actually describing the population. Okay, that's why it was so important to make sure that everything that we could do to keep that sample as representative of the population as it was describing. Okay, keeps our numbers in line. However, there might be some dissimilarity, as we saw in our warm-up. Okay, there's no guarantee that it's going to match exactly to what's happening in that population. Okay, so most samples are likely to provide an answer that's within 10% of the population answer. And the population answer is expected to be within 10% of whatever that value the sample gave. Okay, so you can make a pretty good guess about that population value. We're going to see how the sample size directly impacts that. So right here I have a sample, a population that we're going to represent here. And we see these smiley faces and we see these X's. Now, there are a total of 400 characters in this entire population. The smiley face is going to represent people who do not carry a gene for some disease. Okay? And the X's, they are going to represent people that do carry a gene for the disease. And we know that within this entire population, 40% carry the gene for the disease. So, of those 400 characters, what would that be? 40%? I think 160 of these characters are X's. Right? So that's representing the entire population. Keep those numbers in mind. Now, if you were to randomly sample from within this population, let's say we're taking samples of size 25. This next slide gives us some possible samples. All right, so our first sample right here, we take a sample of 25 randomly selected, and you can see that in that sample there, 12 of those 25 came back as X's, that they carry the gene for the disease. 12 divided by 25, that's 48%. That's a little bit higher than what we know the entire population is. We said that across the entire population, 40% are X's. Okay, now this is 48%. That's okay. That's within the realm of what we would expect. So we throw those back into the population. We randomly take another sample of size 25. And in this case, only 9 of our 25 are X's. So we see that's 36%. Okay, that's a little bit below the 40%. Put them back in, do another sample. Our third sample here, this was 10 out of 25. This is exactly what we expect from the population. There's no guarantee that it's going to match exactly, but in this case it does. Okay? And then our fourth sample that we take, only 7 out of 25, so 28% of our fourth sample carries the gene for this disease. Now you can see that each sample gave us a different answer. Okay? That it may or may not match that population answer exactly, but they're all relatively close to what we would expect in the entire population, which was 40%. Well, we have a rule here that if we were to take a bunch of these samples of the same size, then we can make some conclusions, and we have some certain equations that we can follow along. Now, these conditions I mentioned are linked on the top of the page for today's lesson, and in the next couple days we'll have some homework questions that will reference these conditions. And really, you'd like to make sure that every problem that you have, okay, that you satisfy these conditions. Okay, kind of like what we saw with some of the probability questions, where if you don't know that you have a independent or you have selections that are independent of each other, then you can't use those equations. Well, same kind of thing here. You need to know that these conditions are met in order to use these equations. So our first rule, okay, there exists an actual population with a fixed proportion. So in our example with all those smiley faces and X's, okay, we had an entire population and we knew that 40% were X's. Okay. Or there are some kind of back channels that you can also satisfy these conditions. There exists a repeatable situation for which a certain outcome is likely to occur with a fixed probability. Okay. The second condition that needs to be met, you need to be taking this sample randomly. Okay, it doesn't have to be a simple random sample. However, you could use like those stratified methods, systematic methods, all those different techniques that we talked about in the first semester to select your sample from the population. Okay, you could result in some pretty significant bias if you're not careful with how you're drawing your sample. Okay. The other way, if the situation is repeated numerous times, okay, with the outcome each time independent of all other times. Okay, so if it's not necessarily random, or if it's doesn't make sense for that scenario, there's another back channel for kind of satisfying that condition. Lastly, kind of like what we saw in the warm-up, we need to know that the sample size is large enough. So sample size, or the number of repetitions, is relatively large. Now that's a very ambiguous term. So we're going to kind of quantify that as large enough to see at least 5 of each of the 2 possible responses. All right. So in this case, we're taking a sample size of 25, and we saw that in all of those we had at least 5 of each of them. Now that doesn't have to happen, but across a sample size of 25, you could have seen at least 5 X's and 5 smiley faces. Now, getting into the equations here, okay, if you've satisfied all 3 of those conditions, to define this rule for sample proportions, okay, if numerous samples or repetitions of the same size are taken from the frequency curve made from the proportions from various samples, it will be approximately bell-shaped. That bell-shaped curve, you know, is the normal distribution. And the mean of the true proportion from the population will be the average of all of these sample proportions. And the standard deviation for that will be found using this equation right here. The standard deviation will be equal to the square root of the true proportion times its complement. Okay, this complement right here, we know that we have only 2 possible outcomes. Oops. Here's our complement right there. So that's 1 minus p, and then we're dividing by that sample size. Okay, so we could look at this as an equation here. Our standard deviation is equal to the square root of our true proportion, which we're going to represent with p, times its complement, 1 minus p, divided by the sample size, n. Okay, now this equation is going to be pretty important as we set up this normal distribution, or this bell curve. Okay, saying that of all of those samples that we're taking, okay, they each have their own sample proportions, p hat. There's a difference here between when we're talking about the population proportion is p, the sample proportion is p hat, with a little hat on top of it. Okay, so when we're talking about the X's and the smiley faces there, we knew that the population proportion was 40%, 0.40. Okay, but we saw, like our first sample that we took of size 25, okay, I think its proportion was 48%. Well, that would be p hat 1, and then p hat 2, and then p hat 3 all had their own sample proportions. What this rule says is that the mean or the average of all of those sample proportions will become P, the population proportion. And the standard deviation for that distribution will be found with this equation right here. Okay? So here's P right there at the center of this bell curve. Okay? This rule says that all of those sample proportions will fit this bell curve. Let's take a look at an example to wrap up here. We have the same values as our X's and smiley face example. Let's say that 40% of all voters in the US favor candidate X. Pollsters take a sample of 2,400 people. What sample proportion would be expected to favor candidate X? Well, the sample proportion could be anything from a bell-shaped curve with a mean of 0.40. There's that 40%. Okay, so we put the 40% as our p-value for the standard deviation. 1 minus that 0.4 or 0.6 goes right there as the complement, divided by that sample size. We're taking a sample size of 2,400 people, and we get a standard deviation of 0.01. So if we start to visualize this bell curve, okay, we did a lot of work in the first semester with the normal distribution. This rule says that our population proportion should be right there at the center, 0.40, and then our standard deviation step size we just calculated to be 0.01. So that means this is 0.41, this is 0.42, this is 0.43. I'm running out of space there. You get the idea. And going to the left, 0.39, 0.38, 0.37. And because it fits this normal distribution, we could apply our empirical rule to bring in some probabilities. Okay, remember the empirical rule, 68, 95, 99.7. Okay, we are 68% sure that our sample proportion is going to be between 39 and 41%, okay, within one standard deviation. Okay, so right there to there. 95% chance it's within two standard deviations, 38% to 42%. And we're almost certain, 99.7% sure, that it's within three standard deviations. Okay, so that 37% to 43%. Okay, so if we got a sample leading up to this election and 42% of the voters favored this candidate, well, 95% of the samples that we would take of size 2,400 are going to be between 38 and 42%. Okay, so that's pretty reflective of the population as a whole. Okay. Now, we're kind of working backwards here because we knew what that population value was. Okay, we knew 40% of all voters favored this candidate, and that's not usually true. Okay, we don't typically know the population value before our sample value. Okay, so that's what we'll be working towards in the next couple days, is to use that sample value to hopefully get some perspective about how accurate that population value is.